Hi everyone, my name is Ramy Shahin. I'll be talking about automatic and efficient variability-aware lifting of functional programs. This is joint work with Marsha Chechik from University of Toronto. So this work has been mainly motivated by the analysis of software product lines. So I will start by introducing what SPLs are. So a software product line is a family of related software products developed together from a common set of artifacts. And the unit of variability between those products and each other is a feature. Each feature can be either present or absent in each of the products. And because of that combinatorial nature of features, the number of products grows exponentially with the number of features in the worst case. This is an example of an annotative software product line where feature-specific code is annotated using C preprocessor macros. In this example, we have two features, FA and FB, and according to the semantics of the C preprocessor, each line of code in this program is assigned what we call a presence condition, which is a propositional formula over features defining the set of products in which each line belongs. So all the lines with presence condition of true are present in all product variants. The line with presence condition FA is only present when feature FA is included in a product, while the line with presence condition not FA is only present when the feature FA is absent or not included in a product. And similarly for feature FB. So given a product line, we can instantiate products out of it using what we call feature configuration. And a feature configuration is just the set of features that we would like to be included in a product. So in this example, with feature configuration FB, we generate the product on the right-hand side from the software product line on the left-hand side. And again, this is just according to the semantics of the C preprocessor. So the problem we're trying to solve is analyzing product lines or how to analyze them. As I mentioned, we can instantiate a product instance out of a product line given a feature configuration, and we can feed that product instance into any off-the-shelf analysis tool like a model checker or a type checker or a static analysis tool. And we get a result that corresponds to that specific product instance. But is it possible to analyze the whole product line instead? And the most trivial and straightforward approach would be to instantiate all product instances from the product line and feed them one by one to the analysis tool. And the results are going to correspond, we're going to have one-to-one correspondence between results and product instances. But as I mentioned earlier, this is not going to be feasible because in most practical cases, the number of product instances is going to be huge because, again, this grows exponentially with the number of features. So to give you an example, the Linux kernel is a product line with about 10,000 features. So instantiating all product instances is just impossible. So the practical approach that has been followed for the last decade or so is to take an existing analysis and redesign it and re-implement it so that it becomes variability aware, which means it can actually handle the kind of variability available in software product lines. Some examples of this approach are TypeChef and SuperC, which are both variability-aware C language parsers. TypeChef is also a variability-aware type checker. Feature transition systems and SNP are examples of variability-aware model checking, and SPL Lift is a variability-aware data flow analysis framework for Java programs. The biggest drawback of this approach is that all the effort put into redesigning and re-implementing the analysis is analysis specific. So you need to take this like individually at one analysis at a time, and because this process takes a lot of time and effort, it's also error prone. What we're introducing instead is lifting the language in which the analysis is written. Because at the end of the day, an analysis is a computer program written in some language. So if we lift the interpreter or the compiler of that language, then first of all, we don't need to modify the original analysis at all. And also, all analyses written in that language are going to be lifted for free. And actually, we applied that approach to Datalog-based analyses. We have an FSE 19 paper on this, and also we have a Paddle 20 paper on the details of the variability-aware Datalog engine that's used in the process. In this OOPSLA paper, though, we're trying to go beyond Datalog. And in particular, we're trying to lift a Turing-complete functional language that's an extension of PCF. So actually, we're adding pattern matching, polymorphic lists, and polymorphic pairs to PCF. And in that language, we're writing, we wrote a set of analyses. And in the paper, we presented a couple of approaches to lifting those analyses. The first, what we call shallow lifting, wraps an analysis into a variability-aware version of it. And the second approach actually rewrites the analysis program. And again, because this one is more intrusive, we call this deep lifting. And we are evaluating both shallow and deep lifting against brute force analysis on the BusyBox C language software product line that includes 504 C source files. So in functional languages, we start with values and variables. So a variability-aware variable can have multiple values at the same time, each in a specific set of products, and those sets are defined by presence conditions, like in this example here. But for this to make sense, there are two invariants that need to hold. First, the lifted value has to be defined in each valid product, which means the disjunction of the presence conditions of those individual values has to correspond to the set of all valid products, what we call phi here in this equation. But this is not enough. Actually, it has to be defined in each valid product exactly once. And this is what the disjointness invariant is saying. All this invariant says is the pairwise conjunction of presence conditions within a value has to be unsatisfiable, which means the sets corresponding to those presence conditions have to be disjoint. In functional languages, functions are values. For example, foo here is a function that takes 3 integers and returns an integer. So we can apply the same var type function to this function type. So foo prime becomes of this type, and one example value of foo prime is foo with the presence condition of true. But the problem now is how can we apply foo prime to variability-aware values, or variability-aware integers in this case. So we need a new lifted function application operator, and this is what this spaceship operator here is doing. So if you're familiar with Haskell, you will recognize this type signature and from the applicative type class. And actually var is an instance of the applicative type class. And we just use carrying to apply lifted functions to multiple lifted arguments. So shallow lifting is all about taking functions as black boxes and using the lifted function application operator on lifted values. So in this example, all the lifted function application operator is doing is it's generating the cross product of the arguments, in this example x, y, and z. And as we can see here, each row in this table has a presence condition, which is the conjunction of the presence conditions of its individual values. And since presence conditions denote sets of products, then unsatisfiable presence conditions can be just removed right away because they correspond to the empty set of the products. And we're now left with 4 input vectors, and we can pass those one by one to the original foo function, and the result is going to have its corresponding presence condition. As I mentioned, shallow lifting is a black box approach. It does not care about the implementation of the function. So what if foo is actually internally calling bar and baz, and it's passing z to baz? So using the shallow lifting approach, we will end up calling baz internally from within foo 4 times, but actually it's going to be called 4 times on the exact same argument. So baz5, this expression is going to be evaluated 4 times, and we would like to eliminate this kind of redundancy. In order to be able to do that, we need to push lifted function application inside the body of the function, which means we actually need to rewrite foo in this way here. And again, the benefit of deep lifting is, first of all, we can keep pushing lifted function application as deep as we can, and the more we do that, the more sharing we can leverage. So we actually evaluated the 2 approaches, shallow and deep lifting, against brute force, which means just instantiating all product instances and applying the analysis to each of them. We did that for 6 different analyses. I'm only showing the results of one, the case termination benchmark analysis. So in this graph, the x-axis is the number of unique product variants. The y-axis is analysis time in seconds, and both x and y, the x and y axes are both in log scale. So as we can see early on, with a very small number of product variants, brute force is outperforming both shallow and deep lifting. But as we reach the point of about maybe 5 product variants, shallow lifting starts outperforming brute force. And when we reach the point of about 30 or 40 product variants, deep lifting starts outperforming both. And with the exception of the outlier we see at about 300 variants, this behavior goes steadily. So at around 900 variants, we can see that deep lifting is about 2 orders of magnitude faster than brute force, and more than an order of magnitude faster than shallow. At around 3,000 products, we can see that deep lifting is about 3 orders of magnitude faster than brute force, and about an order of magnitude faster than shallow lifting. So to summarize, in this paper, we presented correctness criteria for variability-aware functional programs. We presented 2 approaches to lifting functional programs, shallow lifting, which is black box, lightweight, and deep lifting, which involves program rewriting. We provided correctness proof sketches. We outlined the design of program rewriter and variability library, both written in Haskell. And we evaluated the whole framework on 6 analyses applied to the BusyBox C language software product line. For future work, we're planning to expand the subset of Haskell that we currently support, probably to include type classes. We also would like to have a more elaborate treatment of recursive data structures, going beyond lists and pairs. And we also would like to formalize the rewrite rules and their correctness proofs. Thank you so much, and I'll be happy to answer any questions you might have.